All right, let's dive right in. Today, we're going inside the machine to really get a look at the building blocks of a robot's intelligence. I mean, we see robots doing all this incredible stuff, but what's actually going on inside their heads?
That really is the big question, isn't it? It's not just about gears and motors. It's about that complex, invisible process that lets a robot see the world, make a plan, and then act on it. How does it take this massive flood of raw data and turn it into one single, meaningful decision? Let's find out.
So, while you and I might call it a brain, the technical term is computing elements. This is the absolute core of its intelligence, that powerful mix of hardware and software that takes in all the information from the world and decides what to do next. It's mission control for every single thing the robot does.
And the best way to really wrap our heads around these computing elements is to build one ourselves, conceptually at least. So let's start putting together the fundamental components that give a robot its smarts.
First up, we need the engine, the processing power. This is where the actual thinking happens. And just like any good team, a robot's brain has two main kinds of thinkers. You've got your general coordinator, and you've got your focused specialist.
At the very heart of it all is the CPU, the central processing unit. Think of this as the project manager for the entire robot. It is constantly juggling tasks, taking in data from sensors, running the main programs, and shooting out commands to the arms, the wheels, whatever. Its number one job is to make sure every single part works together like a well-oiled machine.
A perfect example? Go look at a car factory. That incredible precision, where a robot arm welds a car door in the exact same spot time after time, that's the CPU, just flawlessly executing its instructions and coordinating this complex dance of machinery.
But here's the thing. The CPU, as brilliant as it is, can't do it all. When the robot needs to process a mind-boggling amount of visual information or recognize really complex patterns all at once, well, it needs to call in a specialist.
And this really highlights how differently they think. The CPU is a master of doing things one after another, in sequence. But the GPU, the graphics processing unit, is a totally different animal. It's a master of parallel processing. It's built to do literally thousands of calculations all at the same time. This makes it the perfect specialist for understanding the visual world.
And this is where the GPU is an absolute rock star. An autonomous car is just being flooded with data from cameras and sensors. A CPU would be completely overwhelmed trying to process that step by step. But a GPU, it just chews through all that information instantly to identify a stop sign, track a person, and keep the car in its lane. The GPU is the specialist that makes self-driving even possible.
Okay, so we've got our processors, we've got our thinkers. But a brain is pretty useless without knowledge, right? This brings us to the next critical piece we have to build, the robot's memory, and the system that keeps it all organized.
Like us, robots have different kinds of memory. There's the short-term memory, or RAM, which is kind of like a mental workbench for whatever the robot is focused on right now. And then you've got long-term storage. This is its library of knowledge. It holds its core programming, maps of its environment, and basically everything it's ever learned.
Think about a warehouse robot. It has the map of the entire building saved in its long-term storage. But when it gets an order, it pulls that map into its short-term memory, its workbench, to calculate the most efficient path to that item, right here, right now. It's that powerful teamwork between stored knowledge and immediate processing.
Now, having a huge library of memory is one thing, but you need a librarian to manage it all. And that's exactly where the operating system, or OS, comes into play. It organizes all the data, coordinates what the CPU and GPU are doing, and just makes sure all the robot's different programs run smoothly. And this isn't some abstract idea, by the way. There are real-world systems out there like ROS, the Robot Operating System. It acts as the backbone for countless robots today, giving developers a standard framework to build all sorts of amazing things on. All right, we have processors, we have memory, and we have a manager. Our robot brain is almost complete. But to be truly intelligent in the modern world, it can't be isolated. It needs to be connected to the outside world. This brings us to the final piece of our puzzle, networking. A robot's intelligence rarely just exists inside its own body. It's often extended way beyond that. Think about collaborative robots in a factory, getting instructions from a central system. Or delivery robots getting live navigation updates from the cloud. Or maybe the coolest example, the Mars rover sending scientific data across millions of miles of space right back to us on Earth. This network is its connection to a much wider world of information.
So, we've assembled all the pieces: the CPU, the GPU, memory, the OS, and the network. Now let's just step back for a second and look at the intelligent system we've created.
So, let's just recap the brain we've built. The CPU acts as the coordinator, like in an industrial arm. The GPU is our visual specialist, crucial for an autonomous car. Memory serves as the entire knowledge base for a warehouse robot. The OS is the manager, keeping a complex humanoid assistant running properly. And the network is the communicator, linking the Mars rover all the way back here to Earth.
And that's the ultimate takeaway here. It's this powerful combination of all these computing elements that elevates a robot from just being a simple machine that follows instructions into an intelligent system that can genuinely perceive its environment, make its own decisions, and even adapt to new challenges. This leaves us with a final, fascinating question. As these components, these robotic brains, become exponentially more powerful and interconnected, where do we draw the line? At what point does a complex program machine start to become what we might actually call a truly adaptive intelligence? It's a profound question for our future. Thanks for joining me.